Good morning, this is Mr. McMurray, and we're a little day behind here, but that's okay. We'll get there eventually, right? And so we are posting for, this is actually Tuesday morning, but Monday's assignment. Sorry about that. We had a change in what we're going to do today, and things went kind of hectic yesterday. All right. So, conservation momentum worksheet. Here we go. It says if two objects collide, Newton's third law tells us that for every action force, they're an equal reaction. So, for the two objects, that means we'll say force 1, which is the force on the first object, is equal to the force on the second object. So force 1 is equal to force 2. Now, since they can only collide for the same length of time, one can't hit the other one longer than the other one hits it. So we know that time 1, okay, is equal to time 2. All right. So if they experience the same force for the same length of time, their impulses are also going to be equal, which means we can say down here the impulse of the first one, which is force 1, whoops, do that, times time 1 is going to be equal to force 2 times time 2. All right, that should be a capital F there, but we'll change that. All right, so basically the impulse on one object is equal to the impulse on the other object. Now, since we also know that the impulse is equal, that means their change of momentum is equal also. So we're going to say that means the formula for change of momentum is mass times change in velocity. So that tells us that mass 1 times delta V, I haven't figured out how to do a Greek letter delta yet, velocity, okay, and that would also be 1, would be equal to mass 2 times the velocity 2, and that would also going to be equal, all right? And so their change in momentum is also equal. Now, if their change in momentum is equal, then this explains why we can have conservation of momentum. Basically, in other words, if one object loses a certain amount of momentum, then the other object must gain it. And that way, the total momentum of the system, the two objects, is going to stay the same. And that's what it said down here is a law of conservation of momentum, or law of momentum conservation, whichever, same difference. But so if one object loses momentum, the other object in the collision must gain it in order to make up for that. Now, we're going to do a quick example down here on the bottom of the page. So for this, it says that we have a goal line right here. Whoops, not a very straight goal line, but that's okay. Over here, we have a fullback, all right? And he has a momentum, a mass of 50 kilograms, and he is moving at a speed of 2 meters per second. All right. On the other side of the line, we have a linebacker. All right. Who has a mass of 60 kilograms, and he is also going 2 meters per second. However, this guy is going the opposite direction. So I'm going to go ahead and put that down here. And since he's going the opposite direction, we're going to say he's a -2 because he's going the opposite direction of this one. All right. So this guy is moving this direction and trying to get in the end zone. And the linebacker is going to meet him, trying to keep him out. Okay. Before the reaction, all right, we do 2 times 50 gives us 100 units of momentum. All right, so on this side we have 100 units of momentum. actually kilograms times meters per second, but I'll write that down. And on this side, we have negative 120. Okay, so the net momentum before they hit is 20 units. And what direction is it going to be in? It goes in the direction of the bigger number, so it's going to go this way. So the momentum is greater. And after they hit each other, now they hit each other, they are going to still continue to move this direction with 20 units of momentum, which means that the fullback is not going to get over the goal line. All right. All right. And so if there was a difference in momentum of negative 20 before they hit, and after hit, there's also going to be a a momentum of 20 kilogram times meters per second into the back into the football field. All right. This is why, since running backs tend to be smaller than linemen and linebackers, they tend to either try not to hit them and zigzag around them using the inertia and therefore the harder ability of the lineman or linebacker to change directions to juke them out and get into the end zone without hitting them. Or the other way is, the only way this guy could get through that guy is to pick up the speed. If he had been going 3 meters per second, for example, that would be 150 units, and then he would have bowled over the linebacker. So either by going faster or just avoiding the lineman altogether is about the only way he's going to get in there. All right. All right. Now, what I'd like for you to do is do the rest of these, answer the questions. I think we've kind of gone through a lot of these like that. But, all right, let's look at number 4 and 5, though. We'll answer those, and I think the rest of them you can kind of figure out. But here we go. It says if a 5 kilogram bowling ball is projected upward with a velocity of 2.0 meters per second. So first of all, this here is our mass, and it was at rest, so we could actually argue this is our change in velocity. Okay, it was going 0, now it's projected upward with a velocity of 2.0 meters per second. Now, we know that for every force that put the force on this, it's going to put a reaction force on the Earth. All right. So we can calculate this. We know what the mass of the Earth is right here. Okay. And we can set a formula because we know the change in momentum of the bowling ball is going to be equal to the change in momentum of the Earth. All right. So if we put that in our formula, the mass, which is 5 kilograms, times change in velocity, which is 2.0 meters per second, is equal to the mass of the Earth, which is 6.0 times 10 to the 24th. That's a big number because the Earth is humongous. All right, times delta V. All right, we want to solve for the change in velocity for the Earth, the recoil velocity of the Earth. All right, we just do 5 times that gives us 10, and divide it by 6.0 times 10 to the 24th. Okay, I'm sorry. All right, there we go. Sorry, I was looking at the wrong problem. Okay, that's all right. Okay, so we get 5 times 2 is 10, divided by that, and you end up with an answer of 1.7, at least after you round those digs, times and 10 to the negative, because we divided by 10 to the 24th, so we end up getting 10 to the negative 24th. Okay, now meters per second. Okay, sorry, my bad. That should be meters per second. Okay, now if we wrote that out longhand, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23. Meters per second. All right, now this is why we don't really notice when the Earth doesn't really pay much attention to us. We exert or push on the Earth It does change the Earth's velocity, but obviously not enough to notice, okay? Not to mention all the people in different parts of the Earth doing the same thing at the same time, it would probably cancel out anyhow. But even if you got all the people on Earth in one spot and jump on it, the Earth is so massive that the change in its momentum is going to be, and change in its velocity is going to be very, 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 very small, okay? All right. Which answers the question above. It says if a ball is projected upward from the ground with 10 units of momentum, what is the recoil of the Earth? It's going to be the same except for the opposite direction, so it's going to be negative 10. I'm sorry, I guess down here this should have been this one should have been negative, that number. Okay, sorry, my bad. All right, now, anyhow, the Earth would feel negative 10 units. It's going to go in the other direction. And the question is, do we feel this? And the explanation would be no, because the Earth's mass is so large, the change in velocity is such a small number. And that's what we actually calculated down here at the bottom. Okay, it's so small we would not even feel that. All right. Okay, I think the rest of them, if you can answer on your own, and have a good day.